Assalamualaikum warahmatullahi wabarakatuh. So hello guys. Our group will present our materials about inner product. It's from the subject of linear algebra, class Q, from Mr. Christopher Fahim. This is the assignment. Next. So first of all, let's introduce ourselves. My name is Fehru Putra with for last number 1040.
My name is Muhammad Farisan Avianto. The last three-digit number is 125.
My name is Fajar. The last three digit is 145.
My name is Reza A, Baihaqi with last digit 15.
My name is Melvin Alamsyah with the last digit number is 0.
My name is Jiryan Farokhi with three last digit number is 102.
And my name is Irvan with my last digit number is 44.
So this is the outline of our materials. So first of all, we will discuss about the inner product, both the definition and example, and then we move on to norm, orthogonal, and lastly orthonormal. Next. Okay, let me to explain about the definition of inner product. So basically, an inner product is a product. Inner product is on a vector v over field f. Real R or complexity is a function that maps two vectors to a scalar. So dot product is defined by the v times v maps to the field of f. For the axiom, for our vectors u, v, and v, the elements of v, and the scalar c, the elements of field f, we have three axioms. The positive definiteness. The positive definiteness say that the inner product of v and v is equal and greater than 0, and inner product of v and v is equal to 0 if only if v is equal to 0. Second is the linearity. So the inner product of u plus v and w is equal to the inner product of u and w plus the inner product of v and w. And also the inner product of c times u and v is equal to c times the inner product of u and v. And lastly, the conjugate symmetry. The inner product of u and v is equal to the inner product of v and u for real factors. Next.
Okay, so here's just an example for inner product. Tadi kita udah tahu mengenai definisi inner product. Jadi di sini ada contoh soal yang dimana soalnya adalah untuk membuktikan bahwasannya inner product FG equal to integral A to B fx multiplication gx dx is an inner product. So we need to proving, let's say we have FGV belongs to C, where C is C A to B and C belongs to real numbers. Terus yang akan kita dapatkan pertama adalah inner product FG equal to GF. Nah, dari sini kita sebenarnya sudah tahu bahwasannya karena kita di bilangan asli, maka kita tidak maka sudah dipastikan bahwasannya untuk syarat pertama itu sudah memenuhi. So this for the axiom 1 is satisfied. Next we need to proving axiom 2, where inner product f term if f plus k w equal to a to b fx multiplication gx w x dx. Nah, karena di sini masih kita penduduk dalam kebilangan reals, maka kita akan operasi seperti biasanya, nah, sesuai di PPT, sehingga dapat seperti berikut. So therefore is axiom for number 2 is satisfied. Next, number 3. Number 3 is let's sesuai yang ada di PPT ini, karena C itu adalah any scalar di bilangan real, maka kita bisa keluarkan dari integral tersebut sehingga kita tidak dapat C sama dengan C A, C integral dari A ke B fx tambah gx dx, dan by definition integral A menuju B fx gx dx itu adalah inner product fg. So we get C inner product fg. Karena nomor 3 sudah memenuhi, sehingga kita akan lanjut untuk pembuktian nomor keempat. Where proving for number 4 is inner product f equal to A to B fx multiplication fx dx equal to A integral A to B fx power dx. As we know from the property of integral, we have f in the inner product f is greater than 0. Jadi sudah dipastikan dari properti integral, karena f kuadrat itu suatu non negatif sehingga kita dapat bahwasanya inner product f, f itu lebih dari 0. Sehingga for syarat keempat is satisfied atau memenuhi. Yang nomor 5 adalah inner product f equal to 0 if only if f equal to 0. Karena kita bentuknya nil if only if, maka kita perlu membuktikan dua-duanya. Maka dari itu mari kita mulai dari left side terlebih dahulu. Right side to left side. Jadi dari premis kanan kita memiliki f sama dengan 0. Nah, sedemikian hingga f inner product f, f sama dengan A integral A sampai B fx power dx equal to 0. So this is proving for this statement is satisfied. Karena dari kanan ke kiri sudah terbukti benar, maka kita lanjut ke left side to right side, dan di mana kiri ke kanan, kemudian dari kiri ke kanan. Dari kiri kita memiliki premis inner product f, f equal to 0. So as we know, a integral a to b fx power equal to 0. From the integral property, we have fx equal to power 2 equal 0. Because fx power 2 is non-negative function, therefore fx equal to 0. Nah, setelah kita sudah membuktikan dari 5 aksiom dari definisi inner product, maka bisa dibuktikan bahwasanya inner product fg ini adalah inner product. Oke, next.
Okay, here I will explain about the norm. Here I put the definition from the materials. The norm is a function that measures the size or length of a vector in a vector space, and it assigns a non-negative scalar to every vector, capturing its magnitude while ignoring its direction. So basically the norm is ignoring its direction. Mathematically, a norm are symbolized with the double absolute value with the inside of it x is satisfies these properties for any vectors x and y and scalar of c, which the properties of the norm are three. Those are is the first is non-negativity. The first is when we have the norm of x greater than and equal with 0, and the norm of x is equal with 0, if and only if the x is equal with 0. So it's the relation of it. And the second of the properties is the scalar multiplications. which is when we have the norm of the Cx, it's equal with the absolute value of C times with the norm of X. The third of these properties, it's called with the triangle inequality, which is the norm of X plus Y is less and equal with the norm of X plus the norm of Y. After that, I put some examples of the norms. I only put 3 examples here. First is Euclidean norm, that also called with L2 norm. This norm is the most commonly used norm, also known as the 2 norm, which is defined as the norm of X with a digit or the parameter 2, which is equal with the square root of x1 squared, x2 squared, x1 squared plus x2 squared plus etc. until the xn squared. And we here have the interpretation, which is Euclidean norm measures the straight line distance of a vector from the origin. For the example here, I put coordinate with x. Oh, sorry, not coordinate. I mean the x has the value 3 and 4. Then so the Euclidean norm of the x is the square root of 3 plus 3 squared plus 4 squared is 5, and the 5 is the Euclidean norm of the x. And then the second is Manhattan norm, also called with the L first norm or taxicab norm, which is defined the norm of x with the digit 1 is equal with the absolute value of x1 plus absolute value of x2 plus etc. until the absolute value of xn. So the Manhattan norm have the interpretation like this. It represents the total absolute value of the distance traveled along each dimension. So for the example, I put the x, which is 3 and 4. So the Manhattan norm of the x is the absolute value of 3 plus absolute value of 4, which is we have 7 here. So it's a little bit different with the Euclidean norm before. Okay, the next is infinity norm, which is also called with L infinity norm. This norm takes the largest absolute value among the vector's components that can describe as below, which is we have the norm of x with the parameter or the digit is infinity equal with the max of the range start from the absolute value x1 and then the absolute value of x2 and then so on and so on until the absolute value of xn. So the infinity of norm have the interpretation which it measures the largest extent of the vector along any single dimension. So for the example here, I put the x, which is the value of it is 3n minus 4. So when we calculate the infinity norm of this x, we have the maximum of the range of x itself, which is the maximum value of the range, the absolute value of 3 and the absolute value of the minus 4. And we have the 4 is the infinity norm of the x. Okay, next.
Okay, for the next one is orthogonal. For the definition, suppose that U and V are two vectors in an inner product space. They are said to be orthogonal if the inner product UV equals 0. Note that whether or not two vectors are orthogonal will depend greatly on the inner product that we're using. Two vectors may be orthogonal with respect to one inner product defined on a vector space, but not orthogonal with respect to a second inner product defined on the same vector space. For another theorem, suppose that U and V are orthogonal vector in an inner product space, then norm U plus V power of 2 equals norm U power of 2 plus norm V power of 2. Next. The next one is for the example. We have two questions. For the first one is suppose U1 equals -202, U2 equals 030, and U3 equals 101 on R power of 3. For the question is the set of vector S equals U1, U2, U3 an orthogonal set? So for the answer of this completion is the inner product U1 and U2 equals -2002.030. So we have the result is 0. The same goes on the inner product U1 and U3 equals -202.101, and the result is 0. And U2 and the inner product U2 and U3 same goes before, the result is 0. And so we have the inner product U1 U2 equals the U1 U3 equals the inner product U2 U3 equals 0. So the conclusion is, so the vector S is an orthogonal set. The next one. The next one is, if U and V are two orthogonal vectors, then prove that norm U plus V power of 2 equals norm U power of 2 plus norm V power of 2. The answer of this completion is, based on the definition of norm vector, we get norm U plus V power of 2 equals the inner product U plus V and U plus V. And then we have U, the inner product U and U plus V plus the inner product U V and U plus V. So we have again and the inner product U and U plus the inner product U and V plus the inner product V and U and plus the inner product V and V. Since U and V are orthogonal, that we know that the inner product U plus V, U and V equals the inner product V and U equals 0. As a result, the norm U plus V power of 2 equals the inner product U and U plus 0 plus the inner product V and V. So we have the inner product U and U plus V and V, and then the result is norm U power of 2 plus the norm V power of 2 is proven. Next.
Then, the definition of orthogonal complement is shown by definition 5. Suppose that W is a subspace of an inner product space V. We say that a vector U from V is orthogonal to W if it is orthogonal to every vector in W. The set of all vectors that are orthogonal to W is called the orthogonal complement of W and is denoted by W verb. We say that W and W verb are orthogonal complements. Next. Here's the example of orthogonal complement. Suppose that we have a question, find a basis for W verb, where W is equal to span the set of two matrices like this one. Then we can write W verb is equal to the set of vector X such that the vector X dot matrix 1 minus 5 2 3 is equal to 0. And also the vector of x dot matrix 2 minus 2 1 1 1 is equal to 0. Then by the definition we can write the equation like this: x1 minus 5x2 plus 2x3 plus 3x4 is equal to 0, and so on. Then we can write into the matrix form like this: matrix 1 minus 5 2 3 2 1 1 1 times x1 x2 x3 x4 is equal to 0. Next. After that, we have to find the solution of x1, x2, x3, x4. By using elementary row operation or row, we got the solution like this: x1 is equal to minus 7 over 11s minus x over 11t, and x2 is equal to 3 over 11s plus 5 over 11t, which is as t is any number belongs to R, and x3 is equal to s, and x4 is equal to t. We get the vector of x is equal to minus 7 over 11, 3 over 11, 1, 0, s plus minus x over 11, 5 over 11, 0, 1, t. Then the basis for W verb is equal to the set of two matrices from the vector of x. We can write minus 7 over 11, 3 over 11, 1, 0, and minus 8 over 11, 5 over 11, 0, 1. Or we can write the W verb is the set of two matrices like 7, 3, 11, 0, and minus 8, 5, 0, 11. Next.
Okay, I will explain to you about theorem 6 and theorem 7. So the theorem 6 explain the properties of orthogonal complements in inner product space. Let's break down in 2-3 parts. The first point is W prop is a subspace of V. The orthogonal complement W prop is defined as the set of all vectors in V that are orthogonal to every vector in W. This subsets from a valid subspace of V. This means it satisfies the subset properties closure under addition and scalar multiplication. The next point is the zero vector is the only common W and W verb. There are not exist other vectors except zero that can be shared by W and W verb. This implies that W and W verb are not intersections, or W and W verb are disjoints except at the origin. The next point is the orthogonal complement. The orthogonal component of W verb is W itself. You can see the symbol like W verb equal to W. This is a basic property of inner product space, which shows that W is completely recovered from its orthogonal complement. So, if you take the orthogonal complement twice, you will return to the original space. Next. Let's move on to the theorem 7. In this theorem, which applies these ideas to the fundamental subspace of E. Let E be an N multiplies M matrix. Then the null space of E and the row space of E are orthogonal complements in Rm. The null space is the set of all vectors that satisfy E multiplied X equal to 0. The row space consists of all linear combinations of the rows of matrix E. This orthogonal complement means that every vector in the null space is orthogonal to all vectors in the row space. The null space of ET and the column space of E are orthogonal complements in Rn. The null space of ET is the set of all vectors Y that satisfy ET multiplies Y equal to 0. Column space of E is the set of all linear combinations of the columns matrix E. This orthogonal complements means that every vector in the null space of ET is orthogonal to all vectors in the column space. The connection between the term 7 and term 6 is about how orthogonal complements are crucial in understanding the geometry of matrices and their subspaces.
Okay, I will explain about orthonormal. So the definition of orthonormal is if we have U and V element of inner product space. So if U and V are orthogonal vectors and norm of U is equal to norm of V is equal to 1. So if the norm is equal to 1, then U and V are called orthonormal vectors. So for the example, let's say we have U is a vector of 1 and 0 and V is vector of 0 and 1. So if we want to prove the orthonormality of the two vectors, we should prove the orthogonality first. So let's say we have the inner product rules is dot product. So U dot V is equal to 1 times 0 plus 0 times 1 and is equal to 0. And then we want to prove the normality. I mean the norm is equal to 1. So so the norm of U is equal to square root of 1 square plus 0 square is equal to 1, and also for the V. So both of them have norm equal to 1. So we can see that it 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 is they are orthogonal and the norm of them are equal to 1. So they are orthonormal. Okay. That's all from us. Thank you and wassalamualaikum
Assalamualaikum
warahmatullahi
warahmatullahi
wabarakatuh.
wabarakatuh.
Warahmatullahi wabarakatuh.